Alright, well today we're going to go over Fibonacci's numbers, which here's a bit of a historical background for you. You don't necessarily have to understand this part since it's about breeding rabbits. Okay, so Fibonacci was an Italian in the year 1202, and he solved the following problem. We start with one pair of baby rabbits, one male and one female. Rabbits reproduce once each month. Assume each couple has 2 offsprings, one male and one female. A new generation must wait 2 months to start reproducing. How many rabbit couples do we have after n months? Define a procedure fib that computes that number. Alright, so Mr. Fibonacci came up with this little function here. Fibonacci of 0 equals 0. That means that if you got one rabbit couple in 0 months, you're going to end up with 0 rabbit couples, I believe. Alright, then Fibonacci of 1, then you're just going to get 1 rabbit couple, because, yes, that's about it. Fib of n will equal the fib of minus n1, and the fib of minus n2. Oh, alright, now let me unhighlight that. Okay, so this is the fib, the number of rabbits you're going to end up with, number of rabbit couples you're going to end up with at month n is going to be the number of rabbit couples that you ended up with at the previous month plus the number of rabbit couples you ended up with at the month before that. And that is because I guess because it takes 2 months for the rabbits to reproduce once they're born, something to do with that. I don't actually really understand the historical part of this, but this is a famous famous equation. Alright, so let's define this recursively. Define fib lambda n. And this equation is actually found very often in other parts of maths, not just rabbit breeding. It's lots of patterns fit the Fibonacci pattern. Alright, oh, let me explain this. Okay, so we have here if n is less than 2. Okay, so if n is less than 2, n is either 1 or it's 0, and you'll notice that we always return 0 for 0 and 1 for 1. So we don't have to do 2 separate cases for 0 or 1. We can just say if it's less than 2, then return n. Okay, then otherwise we want to add together the Fibonacci of, well, we can just paste that whole line up there. Okay, that's done. Let's get rid of that. Run it. Okay, let me do fib of 6. This should be 8. Yes, that's right. Okay, so how does that work? So fib of 6 calls fib of 5 plus fib of 4, which calls, well, fib of 5 will call fib of 4 plus fib of 3. Fib of 4 will call fib of 3 plus fib of 2. So we're going to end up with a bunch of little fib of 1s and fib of 0s at the end. And that will have in fact we'll have 8 fib of 1s because our answer is 8, and that's the only way you get any value out of this is once it gets down to 1, then you return 1 for it, and if it gets to 0, of course you return 0. Okay, now this is all nice, but watch this. So like fib of 20, oops, don't, just ignore that warning. Fib of 20 is fine. Fib of 30, see, this is taking some time to get fib of 30, so fib of 31 should take twice as long, because it had to calculate fib of 30 and fib of 31. And then fib of 40 should be why it's just astronomically long. Alright, so let's trace this in well, let me stop this because fib of 40 does take a very long time. Okay, we'll trace this inside this little petite scheme. Paste. Did not paste. That's sad. There we go. Alright, then we're going to do trace fib and then fib of we'll just do fib of 6. Alright, so you see I was telling the truth when I said that fib of 6 called fib of 5 and fib of 4 and fib of 4 called fib of 3 and fib of 2, etc, etc. And so it just goes a bunch of fib of 1s at the end and adds them all together. And of course fib of 0s, which are 0s, that doesn't matter. Okay, so but we can actually define this procedure recursively, and the recursive definition, I mean not recursively but iteratively, and the iterative definition, while being almost impossible to understand, is actually quite fast. So I'm going to define it for you, and then I'm going to vaguely describe it, but not very well. Not necessarily because I don't understand it myself, because I might. Alright, accumulator 1 and accumulator 2. That's what those variables are. Alright, accumulator 1, and then fib it sub 1 n, accumulator 2, plus accumulator 1, accumulator 2. Alright, now let's run this, and I'll show you this. Fib it of 6, remember fib 6, what did that equal? I think that was 8. Fib it of 6 equals no, not equals, okay, then 0 and 1 for our accumulators. Oh, I forgot. Alright, there's a nifty function called sub1 that you can define yourself, which is just takes an argument and returns the 1 minus that. I like to use it. It's better than writing -1 every time. Alright, then fib it of 6 should give us 8. Yes, it does. Now watch this. Remember, the fib it of 40 was very hard for us to do. Oh wow, that's fast. Let's do fib it of 100. See if it's really, really fast. Oh wow. And look at the size of this number, that's huge. Okay, now let me show you what we're doing inside. And we'll try to understand this function together, even though it's very difficult to understand. Alright, so fib it. Let's say fib it of 4. Well, let's find out here. What was fib it of 4? Fib it 4. Well, that equals 3. Okay, so fib it of 4 is going to equal 3. But let's just start that there. So now we do fib it. What is this? So it would go through here, n is not 0, so it will run fib it of sub 1 of n, which is 3. And then it will swap. It will make this accumulator 1 equal to accumulator 2, which was 1. So put that at 1. And then this will be accumulator 1 plus accumulator 2, which here 0 plus 1 is 1. Okay, then we'll do fib it 2. So we got to put accumulator 2 in accumulator 1's place, which is just 1, and then we add those together, which is 2. Now fib it 1 is going to be 2 there, and then 3. And then fib it 0 will be 3 and then 5. Okay, but at this point, fib it of 0, it will say that n is 0, so it returns accumulator 1, which is 3. Okay, so you don't need to understand that. Nobody needs to understand it, but you can go back and try and figure out why, how exactly it's working. and the rationale for it. But here, let me paste this into a little petite chase scheme here. We'll trace it, fib it. Now watch this. Fib it of 8. So oh no, we'll trace 6. So remember, this is 6 here, and look how much junk this has. So do fib it of 6. Oh, that is really nice. Very petite in the number of calls it has to make. So that's why it can happen. Now let's do like 40. Look at that. It only makes 40 calls. So that's why it can run so fast. Alright, so that just shows you the power of iteration. It's a lot harder to understand, but if you really have to get